All right. Well, happy Wednesday, everyone, and we'll go ahead and take a look at today's lecture, and we'll see. We'll see what time we have to get through. So let's see here. Okay. Oops. Just make sure I posted this. I also have to post your next homework assignment, so you can expect that coming soon. Okay, so we left off on Monday talking about the Bayes classifier, and this is what we said. We're going to use Bayes' rule to calculate the probability. What we want to do is we want to say, what is the probability that an observation belongs to a certain category or a certain class if we know the values inside that observation, right? So if we know the values of X inside this new observation, what is the probability that it belongs to class 1 or class 2 or class 3, okay? And so we use Bayes' rule, probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. And so the central part is going to be this likelihood portion, which is, well, if we assume the observation came from this particular class 1, let's say, then what would the probability be that it generates the values that we see in X new? Okay, so if it came from, the red class, what's the probability it generates these values that we have in X new? Or if it came from the blue class, what's the probability it generates these values? Okay, we're going to take that's the likelihood. But we also want to take into account just kind of the overall probabilities, the prior probabilities of any one of these classes. So perhaps the red class is more likely or less likely than the blue class or the green class or something like that. So we want to take that into account, okay? And then this thing on the bottom, this marginal probability, this only serves to just kind of make sure that our probabilities, when we calculate the probabilities, that they all add up to 1, okay? And so you don't have to worry too much about the marginal probability. It is an important thing because probabilities, when you calculate all the different probabilities, they do have to add up to 1. So that is important. But other than serving that purpose, there's not a whole lot to be gained from knowing the marginal probability. Okay, it really comes down to what's the probability of getting the values that we have in our observation. If it belongs to a certain class, that's the likelihood. And we multiply it by kind of the prior probability of, how likely is that class in the first place. And so what we're doing is we are applying this in the context of a mixture of multivariate normal distributions. So we have 3 multivariate normal distributions. We have class A, which is plotted in red. We have class B, which is plotted in blue. And we have class C, which is plotted in green. Class A is centered at 2, 3, and has this covariance matrix. Class B is centered at 0, 0, and has this covariance matrix. And class C is centered at 2, -2, and has this covariance matrix. And so the observations for class A are in XA, observations for class B are in XB, and observations for class C are in XC. And we combine them all into this big matrix X. All right, and so this is the plot of our generated data in red dots, blue dots, and green dots. And in this plot, I've also drawn kind of the ellipses of the contour lines that is supposed to have generated our data, okay? Showing that the observations, this is where this is centered, it's centered over here, and there's covariance here, okay? We don't know the generating values, okay? The whole point of this is that we're trying to guess which distribution created this data, and we don't know the generating values, and so we have to estimate them. So we're going to estimate the mean of class A, we're going to estimate the mean of class B, we estimate the mean of class C. All right, and that's simple enough. We just take the column means of class A. Here I have the A observations already subset into this matrix XA. But if that wasn't the case, you would, you'd use dplyr, you'd just kind of filter out your observations just to that subset. You'd subset your full data into, class A, and you calculate your column means there. Okay, so this is going to be X bar A, X bar B, and X bar C. And then we're also going to estimate the variances based on these observations. So we have XA, XB, and XC. We're going to get the variance of A, variance of B, and variance of class C. All right, and so when if we take a look at that, the resulting contour lines are a little bit different, okay? The center of the actual observed data is not exactly at 2, 3, but it's centered somewhere else. The center of this data is not exactly at 0, 0, but it's a little bit off, and the covariance is not exactly equal, so we don't have these perfect circles, but we have a slight ellipse, and the center of the green dots is it's a little bit off, not exactly at 2, -2, but a little bit different, and its covariance is a little bit off. Okay, and so this is the the difference between what we've estimated and what we actually know. We defined the generating distributions ourselves, but when we use our model for classification, we're estimating these values. Okay, so we're using the estimates of the mean and variance from our data. Okay, and based on this, we're going to use Bayes' rule to calculate the probability that a new observation belongs to a particular class. All right, so this part's all review, and I hope this feels okay. Let me know if you guys have any questions here. And let me go ahead and give you your very first view quiz answer for today. Very first view quiz answer today is the letter B. B as in bear, B. B is the very first view quiz answer today. Okay, so here is our test case. We're going to put a test case at 0, 0, and we're going to use the Bayes classifier to calculate the probability that this observation belongs to either the red class, the blue class, or the green class. Red is A, blue is B, and C is green. Okay, so what's the probability that it belongs to this? All right, and so just kind of seeing our data and seeing where it's labeled, I think we would say that it's very clearly that we should pick the blue class. We should say category B. Okay, but let's see if our Bayes classifier, if we can kind of get that result using the Bayes classifier. Okay, and so again, the probability that we're going to calculate, what's the probability that it belongs to class A or class B or class C, given the value in X is 0, 0, all right, and all of the training data is, we're going to ask, well, if it belonged to the red class, could an observation in the red class generate, or could this distribution for the red class generate a point at 0, 0? And the answer is, well, it could, but how likely is it going to happen? It's pretty unlikely. It could happen, but it's pretty unlikely. It's outside this third ring, which I think the last ring is, I want to say is at the kind of the 99th percentile or the 95th percentile. I don't know. So it's a fairly low probability. It could, the red distribution could generate this point. Okay. And then we're going to multiply it by, well, what's the overall probability of getting the red distribution? Okay, and then we say, well, what's the probability that it belongs to the blue distribution? Okay, that's going to be equal to, well, if it were from the blue distribution, what's the probability that the blue distribution generates a point 0, 0? And we'd say, oh yeah, there's a very high probability that the blue distribution would generate the point 0, 0. Okay, so the density there is going to be high. The likelihood there is high. We multiply that by the overall probability that it came from the blue distribution. Okay, same thing with the green distribution. And over here with the green distribution, we'd say, it's pretty unlikely. We measure the distance from here to here, and we'd say it's pretty unlikely for the green distribution to generate this. We don't want to say it's impossible because, multivariate normal technically goes from infinity to negative infinity, but it's pretty unlikely that the green distribution is going to generate this point. Okay, and we would multiply it by kind of the prior probability. What's the probability that something comes from the green distribution. Okay, we're going to calculate, that's going to give us the numerators for all of the cases. We would add them up to get our denominator, right? And so to calculate this probability, we can use the normal PDF, right? And so for the normal PDF, the observation we have is 0, 0, okay? And so to calculate this, we're going to do 1 over 2 pi raised to the, here we have, it's 2-dimensional, so it's going to be raised to the 2 over 2, which is just 1, multiplied by the determinant of our variance matrix. So this is the estimated variance matrix for observations in distribution A, raised to the 1/2 power, multiplied by e to the negative 1/2 times the transpose of x, the new observation x minus mu, okay, x new minus x bar sub A. This is the mean for observation A, multiplied by the inverse of the estimated variance matrix, variance A multiplied by x minus mu, okay? And so we can do this when we get the likelihood of getting the observation 0, 0. So what's the likelihood of getting 0, 0 if it comes from this distribution? Again, and the mean and the variance are estimated from the observed data. And this is our number, okay? And we can do this. Now, R already has a function. Well, not, there's a library that you can load for the multivariate normal, and it's going to calculate the density for us. So we can load up the multivariate normal density thing, and we can use density of the multivariate normal, okay? And we're going to get the, and we get the exact same results here. So dmv norm gives me 0.00879539, okay? 8759539, okay? And here we just say, you know, the observation I have, my new observation is 0, 0. X new is 0, 0. The mean that I'm using is the X bar for class A, which we've estimated back here based on our observed data and the variance that we've estimated from our observed data. Okay, so we're going to use that. We're going to say this is my estimated mean and my estimated variance matrix. And we say, okay, what is that value? And it says it's 0.00879. Okay. And then we can say, all right, well, what if it came from class B? So class B, we use the mean of class B and the variance of class B that we've estimated from our observed data. And we get something a lot higher, 0.165. And then we do it for class C. Okay, class C, again, using the mean and variance that we've estimated for from our observed data, we have a very, very small number, something on the order of 10 to the negative 5. Okay, and so so we use this. This is our likelihoods. What is our prior probabilities? Okay, well, our prior probabilities in our example here, they're all the same, because in our training data, we have 90 observations. And in our training data, all 3 classes have 30 observations. So class A, class B, and class C each account for 1/3 of the observations in the training data. So if we didn't know anything about our observed data point, and we said, what's the probability it comes from class A or class B or class C, we would have just said 1 out of 3. Again, if we knew more about the generating process, and we knew that, you know, half of the data points come from class A, or, you know, only 10% come from class C, you know, we could change that about our priors, okay? But here, we'll go ahead and just use 1/3, because that's what shows up in our training data, okay? Now, technically, because all of these have the exact same value for the prior, they're all going to cancel out when you do the calculations for the marginal and things like that. So it's technically not necessary to include them, but just kind of for completeness, I'm going to include them, even though they all cancel out as far as the Bayes rule formula. But you know, when they're all equal, technically they're all going to cancel out. Okay, so those are my priors. These are the likelihoods. And so to calculate the marginal probability, we're going to add up the numerator across all possible classes. And we have 3 classes. We have A, B, and C, or the red, blue, and green. And so we're going to do the likelihood of A times the prior of A, which is one of the numerators. And we do the likelihood of B times the prior of B, which is our the numerator again for the second class. and the likelihood of C times the prior C, which is the numerator for the third class. That's going to give us our marginal probability. And again, the purpose of the marginal is just so that the resulting probabilities will add up to 1. Okay, and so when we do these calculations, we just do the likelihood times the prior, that's my numerator, divided by the marginal. We're going to get 0.005 that it belongs to class A, 0.995 that it belongs to class B, and then, something very small, 9 times 10 to the negative 5. So, 0.00009 belongs to class C. And so, we're basically going to say, 99% probability that it belongs to class B. Is that good? Are there any questions there as far as how we got this using the Bayes classifier, Bayes rule here? Okay, so let's just try this out. Okay, let's try another test case. All right, so here we're going to put a dot out at location 6, 2. All right, and again, here we're using the estimated mean and variance from our observed data, which is a little bit different from the true mean and variance that generated the data points. But we're going to say, all right, what if you observe a data point at 6, 2? Okay, what would you guess? We'd say probably a little bit more likely A, could be green, and almost certainly not going to be blue, right? So this is just kind of from a lot, it makes sense to just do a logic check, all right? Especially when you have 2D data and our eyes are trained to be able to recognize something like this, right? In a very high dimensional setting, this will still work. If let's say you're in 15 dimensions, 20 dimensions or something, the Bayes classifier would still work. It's just our eyes would have a hard time, our brains would have a hard time visualizing and really being able to understand where it should go. Okay, so anyway, these are the calculations. We calculate the likelihood of the observation 6, 2, okay, using the DMV norm, density of the multivariate normal, okay? And so we plug in x nu, the mean and sigma for class A, the mean and sigma for class B, the mean and sigma for class C. And this is going to give me the likelihood that it belongs to A, or likelihood that it belongs to C, or the likelihood that it belongs to B or C. Okay, the prior probabilities, again, are 1/3 for all 3 classes. And we do the marginal by taking the sum of the likelihood times the prior for each of the 3 classes across all possible numerators. Okay, so all of the calculations have been done here, and therefore the probability that it belongs to class A is going to be the numerator, likelihood of A, times the prior of A divided by the marginal, and we get something close to 80%, 79% that it belongs to class A, 79% class A, almost 0, pretty much 0 that it belongs to class B, right? If class B is centered at somewhere around 0, 0 with this kind of variance, what's the probability it's going to generate a point at 6, 2? That's almost 0, okay? And then what's the likelihood or the probability that it comes from class C? It's around 20, 21%, okay? So we've got around 79% and around 21%. And so we'd say class A has the highest probability. Does it mean it for sure came from class A? No, it doesn't mean for sure it came from class A, but based on what we see, we're going to say it has the highest probability that it came from class A. Okay. Here's another one. This one's a little bit, we're a little bit more uncertain now. Okay. We'd say, maybe fairly likely, equally likely that it came from class A or class C. Okay. And so we can try this out. Test case 5.1. So again, the blue class is the least likely here, but it seems, fairly close for being class A or class B. And we do the calculations here. Again, the same type of things. We calculate the likelihoods using the multivariate normal density. And the priors in our case is 1/3 for all of them. And we end up getting around 39% for class A and around 61% for class C, and pretty much 0 for class B. Okay. And so the small changes, are very can drastically change it, right? From going from 6.2 to 5.1 seems to make a pretty big difference here. Okay. So class C has the highest probability. Okay. And then so this one I tried. I said, well, what if we put it right here? Okay, right in between, kind of at the almost like at the intersection of the red, blue, and the green, and we'll see, which one wins here. And when you do the calculations, we get something pretty, fairly equal here, right? So if we put the dot at 2.53, 0.37, which is kind of where this test case is, we get, around 31% A, 36% B, 33% C. So, while class B has the highest probability out of the three, all three of them have, very similar values, which I think makes sense according to this diagram here, as far as red, blue, and green. This one, it seems to kind of make sense, all right? Using our estimated mean and variances that we've gotten here. Okay. All right, so in summary, this is what we have. You're going to just calculate your likelihood and your prior. The likelihood is based on, whatever model that we're using. And here we're using a multivariate normal distribution. And we're assuming that the mean and the variances we can estimate from the observed data. So we say, for class A, we're estimating the mean to be this and the variance to be this. And we're using that to estimate our likelihoods. Okay, the prior is basically the proportion that belongs to a certain class in our training data. We're kind of assuming that proportion holds. And then the marginal is calculated by calculating the numerator across all of the different possible classes and adding them up. And that just ensures that the posterior probabilities add up to 1 across the different classes. Okay, let me go ahead and give you your second view quiz answer today. Second view quiz answer is A. A as an apple. A as an apple is your second view quiz answer. Okay. And all right, and so we can go from the Bayes classifier to the naive Bayes classifier. Okay, the naive Bayes classifier and the Bayes classifier are very, very, very similar. Okay, the key distinction is that we are going to assume that we're going to make the naive assumption that the variables within X are independent of each other. Okay, and so we're going to say if this variance matrix has zeros for the off diagonals, right? So if the variance matrix is basically a diagonal matrix, then all of the X variables are independent of each other. And if they're all independent of each other, then your multivariate normal distribution can be factored into univariate, a product of, one univariate normal distributions. Okay. So rather than having to calculate kind of the full variance covariance matrix, you can just estimate the variance of one variable and then say you have a product of normal distributions. Okay, so we're going to just take the multivariate and we're going to turn it into a product, and this is just a univariate normal distribution. Okay, so why would we want to do this, right? So the naive assumption in the naive Bayes classifier is that all the X variables are independent of each other, right? And almost certainly this is an assumption that's going to be wrong. Like we already kind of know that X variables, and in a lot of cases, are not going to be truly independent of each other, right? That there's going to be some kind of covariance. We know this is a bad assumption. However, by making a bad assumption, you can end up getting a more useful model. Okay. And there's a few reasons for this. One is that if you wanted to do the multivariate normal distribution, you need to have a good estimate of this sigma matrix, okay? And your estimates of the covariances between, say, x1 and x2 or x2 and x3 or your different X variables, your estimates of the covariance could be wildly off if you only have a few observations, right? So if you have this high dimensional data set, you might have only a few observations, and for a particular category, right? So because we're going to kind of subset our data into different categories, and based on that subset, we're going to estimate the covariances, the means and the variances and the covariances for our data. So if you have this high dimensional data set with several different categories, when you subset your data, you might only have a few observations, and then your estimates of the covariances could be quite wrong, okay? Or at least, even if they're not wrong, we know that they're subject to a lot of kind of random variation, right? So depending on the random variation you observe in your data, you could get wildly different covariance estimates, right? On the other hand, if you just give up and you just say, well, you know what, I'm not even going to bother calculating the covariances. We're going to just set all the covariances to 0. Estimating the individual variances, that requires less information, less data. You can still get a fairly accurate estimate of the variances. Okay. So anyway, this is what we're going to do. We're going to just treat our data as having no covariances. We're only going to just estimate the mean of each variable and the variance of each variable, not worry about the covariance at all. And we're going to just say our density is the product of univariate normal. Okay, so this is the data, the distributions that generated our data. Okay, and so as far as our generated data, there's actually no covariance between x1 and x2 in the red distribution, and no covariance between x1 and x2 in the blue distribution, but there's a lot of covariance between x1 and x2 in the green distribution. And distributions here, class C, there's actually a high covariance. When you do the naive Bayes assumption, this is basically how you're going to calculate it. You just say, all right, let's take column 1 for when we subset our data into class A, class B, and class C, and let's just say, let's take the mean of column 1. And so that's going to give me x1 bar for class A, x1 bar for class B, x1 bar for class C. Let's say we take the mean of column 2, and that's going to give me x2 bar for class A, x2 bar for class B, and x2 bar for class C. Okay, and as far as the variances go, I just take column 1 for class A, and we're going to calculate the variance. I also did it for the standard deviations. So variances and standard deviations, you just do kind of one column at a time. So normally, if I did XA all at once, we would get a 2x2 matrix for the variances. But here I'm just doing it for one column. So this is just a scalar value. The standard deviation is just a scalar value. There's no, it's not a matrix here. Okay. So we're just going to get the variances and standard deviations for variable 1 and variable 2, x1 and x2, for all of the 3 different classes here. Okay. And so if we were to estimate kind of the contour lines using the naive assumption, for red and blue, that's okay, because there's no covariance between red and blue in the original data. But we can see for the green class, this is quite wrong, right? Because in the green class, there's actually quite a bit of covariance here, but we're assuming that there's no covariance. And so, the resulting ellipses have their kind of major and minor axis parallel to the x1 and x2 axis. And so if we compare what the naive assumption contours look like versus what the contours would look like if we used a multivariate distribution, we can see, for red and blue, they're kind of similar, but for the green ones, they're quite different, right? Because under the multivariate, we're going to find covariance. Under the naive assumption, there's no covariance, okay? So we know this is no good, but at the same time, it still works out. It still works out, okay? So, again, difference is most pronounced for the green dots. but we're gonna be okay. So let's take a look. Here's test case 0. Under test case 0, we're gonna say, all right, what's the probability it comes from either red, blue, or green, right? And we're gonna do the calculations in the same way. We're gonna calculate the likelihood multiplied by the prior divided by the marginal, okay? The key difference here, as far as the likelihood goes, all right, everything else kind of goes in the same way, is that this, we're not using the multivariate normal distribution. What we're going to do here is we're going to treat it as a product of univariate normal distributions. We're going to do one, a normal distribution for variable x1, normal distribution for variable x2, and we're going to just multiply those two together. Rather than doing the multivariate normal, we're going to just use regular old D norm. Rather than DMV norm for D density of the multivariate normal, we're just going to ask for the density of the normal distribution. But we've got a density for x1, and we have a density for x2, and we're going to take its product. So this is what the calculation looks like, okay? So here our new observation is 0, 0. So x new, we're going to do it first for variable 1, x1. So x new, this one is 0. X new, the first value is 0, okay? And we're going to calculate using the D norm, using the mean of x1 bar and the standard deviation of 1, okay? And to make it kind of to get both variables, x1 and x2, we're going to multiply that by a second D norm, okay? And if you have a high dimensional data set, 4 dimensions, 5 dimensions, whatever, it would just be a product of 4 or 5 D norm values, right? So we do D norm and we have D norm here, okay? All right, is that okay as far as the calculation for getting the likelihood that it belongs to class A, okay? And the likelihood that it belongs to class B is just the same thing. We're gonna plug in, this is 0, x new 1 is 0, and x new 2 is 0. And here we're just using the estimated mean for class B and the estimated standard deviation for class B for variable 1. Estimated mean for class B of variable 2, estimated standard deviation for class B of variable 2. Okay, so on and so forth, and we do that, all right? Let me just show you the comparison, the likelihood of A, likelihood of B, and likelihood of C, okay? This is slide 33. Back here, when we calculated this, okay, these are the numbers. So over here we got 0.0008, 0.165, and here I got 1.64 times 10 to the negative 5. And here over what we have here, this number ends up pretty similar, okay? This is off, okay, 0.00, we have 3 zeros and an 8. And over here we have 2 zeros and a 1. So it's, going from 8 to 12 or 8 to 13 is a little bit different. This one's the most pronounced different, okay? Back here it was on, 1.6 times 10 to the negative 5. Here it's, drastically higher at 0.03 pretty much, okay? And we can see, as far as the picture goes, this one's also, the most drastically different, okay? As far as, where this dot, the test case lies in relation to where the contour lines go, right? So as far as, where the test case lies in the contour lines here, where we're using the multivariate normal, and where it is over here when we're using the naive Bayes classifier, we can see it's most different here, okay? And so when you do the final calculations where you calculate the marginal, you set the priors all equal to 1/3, and you calculate the marginals, we get this, and the resulting values end up, a bit different, although you'd still end up classifying B. Okay, so class B has the highest probability, but class C, which used to have almost 0 probability, is actually the second most probable under the normal naive Bayes assumption, we get, around a 15% probability where it used to be closer to 0, okay? But the naive Bayes classifier is, here's an example where, you're getting, kind of a big difference in the results. But overall, the naive Bayes classifier is actually a useful and a desired model, especially when you don't know how to calculate covariances. Okay, so if you don't know how to calculate covariances for some kind of complex system, the naive Bayes classifier actually makes a lot of sense. Okay, so I have a few minutes left, and so I just wanted to show you just a very, very, very simple example. You're not going to be tested on it or anything like that, but I just wanted to show you like a little demo of how the naive Bayes classifier could be used in something else. Let me go ahead and give you your last view quiz answer for today. Last view quiz answer today is E. E as an elephant. E as an elephant for your last view quiz answer. Okay, and so so we can use the naive Bayes classifier for a like a text classification. Okay, so we could do right, and the way it works is we use what's called a bag of words model. And the bag of words model is a bad model, okay? But it's simple and it makes things easy, okay? And what the bag of words basically is, there's no meaning to basically the order of words, all right? And that's very wrong, right? We know in English where the words are positioned is going to change the meaning, right? But here, as far as bag of words go, is, all meaning comes just from the words that show up in the sentence. Okay, so bag of words, I'd say, is useful for document classification. Like, is this document about sports, or is it about politics? Is it about science or something? Okay, versus something like sentiment analysis. So sentiment analysis is this saying something positive about the thing, or is it saying something negative about the thing, right? So if you say, the team is bad, it is no good, or it is not good, okay? That has a very different from the team is good, it is not bad. Okay, so here, both of these things have the exact same words, right? Okay, as far as how many times does the word is appear, how many times does the word bad appear, how many times does the word good appear? Okay, both of these have the exact same word count. Okay, so both of these, according to a bag of words model, will get the exact same score for whatever model whatever thing you're trying to find. It's going to give the exact same score. Exact same words, according to bag of words, will be the exact same score. Okay, so as far as sentiment analysis, these two sentences will give the exact same sentiment, although one definitely is positive and one is definitely negative with respect to the team. So in that case, bag of words, not very good for something like that. But if we're just talking about, as far as topics go, we just want to know, like, you can say, if you have a document where the word team appears a lot, and the word ball appears a lot, we can say it's probably about sports, okay? If you see another document where the word senator appears a lot or something like that, it's probably about politics or something like that, okay? And so so as far as the bag of words model goes, you can use the naive Bayes classifier, right? And so what the way the naive Bayes classifier works is basically, so what we want to find out is what is the probability that the document is about, say, politics, given, basically the data, which are the word data, and the training data, okay? And so this is going to equal, well, what's the probability of getting the word data given that the document is about politics, okay, times the probability that it was about politics in the first place, divided by the marginal. Okay. So this is the Bayes classifier, right? Okay. And what we're going to do is we're going to just say the probability of the word data is going to be something like the probability that, say, senator appears 10 times times the probability that, or senator appears 10 times given politics, times the probability that team appears once, one time, given politics. And we're basically treating all of the words that appear, okay? And this is, maybe we have, a vocabulary of, say, 1,000 different words, okay? So let's say we have a vocabulary of 1,000 words. So usually you remove all of kind of like what we call stop words or non-useful words. So things like the, a, is, am, all kinds of words that just appear very commonly in English, but don't really provide any kind of contextual meaning. You usually just take those and throw them all away, okay? And so maybe you have a vocabulary of, say, like 1,000 words that could provide meaning, okay? And so what you're going to do is, rather than trying to figure out the covariance, right? What's the covariance between how many times the word senator appears with, the covariance, there's a covariance between, the count of the word senator and the count of the word tree and the count of the word car and the count of the word building or something like that, right? And you got 1,000 different words here, and trying to find the covariances between every single, like the frequency of this word and the frequency of this word and the frequency of this word is going to be like practically impossible. Not impossible, but it's just way too complicated because there's way too many covariances because there's way too many words. And so instead, we're going to just say, you know what? If it's about politics, the word senator is going to appear a lot. If it's about politics, the word trees probably is going to appear a lot less, okay? And if, meanwhile, if we're talking about, I don't know, nature, trees is going to be a lot higher probability and senator is going to be a lot lower probability. And we're not going to worry about covariances between how this word is related to this word and that word and things like that, okay? I mean, so an example where you would have covariances is if you wanted to have a model that did take into account covariances, you'd say, with the word, if this document is about politics, the word house is going to appear frequently with the word white or something like that, okay? Although, so, or I don't know, something about, I don't know, a couple other words that would, like, in this context, these two words appear a lot versus, in other contexts, the two words don't appear that frequently, okay? But we're not going to worry about that. We're going to just say, the probability of each of these words individually, okay? And so, so here I don't even know if this was worth showing you guys with the 2 minutes that I have left in class. But basically, I just did did a simple thing using some children's documents. Okay, so here are three kind of three kind of simple kids books. So there's Green Eggs and Ham. Okay, so in the book Green Eggs and Ham, the word green eggs and ham appear very frequently. Okay, and then there's another book called Go Dog Go, and in that book the word dog appears very frequently. All right, and then there's another book called Are You My Mother? Now, in Are You My Mother, the word dog appears, okay, because one of the characters is dog, all right, but it doesn't appear as frequently as over here, where when you search for dog, it appears very frequently. And under Green Eggs and Ham, I don't think the word dog does not appear at all, okay? And so we're gonna say, you know, if a sentence, we're gonna just treat our documents as sentences, our sentences as documents. We're gonna say if the word dog appears in a sentence, we know it cannot be green eggs and ham. Whereas, you know, there's a decent probability that it's from Go Dog Go, and you know, some probability that it comes from Are You My Mother? Okay, and things of that nature. Okay, there's a boat in this one. I think in Go Dog Go there is boat as well. Okay, boat appears in Are You My Mother, appears in Go Dog Go. And boat also appears in Green Eggs and Ham. So boat appears in all of these words. Okay, so anyway, what we've done is we've gone through and we counted up how many times each word appears. Okay, and so the result is when you do, you know, word probability for green eggs. Okay, so I've gone ahead and removed find, is there boat somewhere in here? Okay, here it is. Okay, so the word boat for green eggs and ham appears with this kind of probability. And so this is how we would calculate the likelihood. We would calculate, you know, what's the likelihood of getting some particular word, in this case, boat, for green eggs and ham. For Go Dog Go, we went ahead and we calculated the probability of getting boat. Okay, and then for Are You My Mother, we calculate the probability of getting boat. Okay, and so we can see, so the probabilities of the words differ based on what you have. Okay, whereas something like the word dog, okay, for green eggs and ham, it has a very low probability. Okay, dog does not appear at all in the book Green Eggs and Ham, but you don't want to give it, even if the word doesn't appear ever inside of a document, you don't want to give it a 0 probability. Okay, because a 0 probability means it's impossible. Okay, and so so anyway, we just give it a low probability. In our case, I think we've arbitrarily chosen a number around, you know, 0.004. Okay, whereas for Go Dog Go, it has a very high probability. If a sentence was generated by Go Dog Go, it has a very high probability that it's going to contain the word dog. And if the sentences was generated by mother, Are You My Mother, it has, you know, a decent, you know, not trivial probability that generates the word dog. Okay, so what we can then do is we can take, you know, some kind of test case. Okay, so here we're going to say here is a sentence, okay, where we've kind of just made up some words. All right, and we say, you know, in this sentence, the word green appears once, the word like appears, maybe not a sentence, but maybe in a document. In this document, the word green appears 1 time, the word like appears 3 times, the word dog appears 11 times. Okay, and you know, all of these other words appear 0 times. Party shows up 4 times or something like that. Okay, and then so to calculate the the classification probability for this sentence, what we're going to do is we're going to take basically this vector of counts. Okay, we're going to take the probabilities and just multiply it or raise them to the vector of counts and then take the product. Okay, and this is going to give us kind of the likelihoods. And so, actually, for the Go Dog, I need to do it for Go Dog Go. Because all we're doing is we're saying if it came from a certain thing, and so based on these probabilities, okay, the one with the highest likelihood, and these all are very small probabilities, you know, on the order of 10 to the negative 100, 10 to the negative 47, 10 to the negative 86. These are all have small probabilities just because, you know, it's the probability of getting some exact sequence of words. But this one definitely has the highest likelihood. And then you can kind of take into account the prior probabilities and the marginal probabilities, and you would end up getting some kind of probability here, okay? There's a bunch of other code inside this file that just does some pre-processing of the text as far as, you know, importing the text and turning them into what we call a corpus of documents and things like that. But, you know, as the way this system works is it kind of scans a bunch of documents and says, you know, we know this document these documents belong to this class. It's about politics, or this document's about green eggs, and this document's about dogs, and this document, you know, comes from another thing. And based on that, we get probabilities that each word appears, and we use that. Okay. So anyway, that's just a kind of a brief example. You don't have to worry about that. I will go over kind of the content of the midterm. We have a midterm next week on Wednesday, and I'll go over that. You know, that's what this document midterm slides is about, and there might be some tweaks there, but I'll go over the content of the midterm on Friday, and we'll see you then. Okay, so we'll end here for today, and we'll see you guys on Friday. And I apologize for the grading of midterm 1 and the great delay that has happened there for midterm 1. So we'll try to get the grading for midterm 1 taken care of. So sorry about the delay, and I appreciate your patience. But yeah, I'll go over midterm 2 on Friday, and we'll see you guys then. So have a good night.